Welcome to my video lesson for Precalculus section 1-4, linear functions and slope. So this section is going to focus on lines and how to work with them, how to graph them, what we can do with them. Okay, so the objectives are to first calculate the slope, then we'll write the point slope form of equation of a line, then we'll talk about the slope intercept form of the equation of a line. Then we'll graph horizontal and vertical lines, and then talk a little bit about the general form of a lines equation. And finally, intercepts to graph and a fun word problem where we can use data to model a linear function. Okay. So first, let's start off with slope. So mathematicians have developed a useful measure of the steepness of a line and have called it slope. Okay, so that's all slope means. It means how fast is the line going up, how fast is it going down. And what it does is it compares the vertical change, we like to call that rise, to the horizontal change, the run, when moving from one fixed point to another along the line. So to calculate the slope, we're going to use a ratio that compares y to x, the change in y to the change in x. And here's my formula right here. So you can see as we go from this point to this point, right, as we move down this line, we're going to get higher and we're going to go right. Okay, so that's the change in y, we're getting higher, over the change in x, we're moving more to the right as we go from left to right on this graph. Okay, so the slope of the line through the distinct points, x1, y1, subscripts, that just means the first point, and x2, y2, is the change in y, the rise, divided by the change in run. And the way we find the change between two numbers, where we start, where we finish, is take where you finished minus where you started. y2 minus y1 over x2 minus x1. Now, commonly, we use the letter m to represent slope. Probably, you would say, why not just s? Well, because the letter M is used because the person who came up with most analytic algebraic geometry, René Descartes, was French, so we use the first letter of the French verb, monter, which does start with an M, which means to rise or to ascend. Okay? So don't always think that the letters in math have to be English, right? They're usually not. So let's use the formula. This formula, y2 minus y1 over x2 minus x1, to calculate the slope of the line passing through these points. So first, let's start with the formula again. y2 minus y1 over x2 minus x1. Okay, well, one of these points has to be the starting point. One of these has to be the finishing point. So let's call this x1, y1, x2, y2. Now it is a good habit to go from left to right in terms of x. So I picked this as the first point because this is -3 and this is 2. So this one comes first, this one comes second if you were going from left to right. It does not matter, and we'll talk about that in a second, but that is a good habit to get into. All right, y2 is 4 minus -1. Hardest thing about this, you just got to be careful with your signs. Okay, x2 minus x1. So that is 4 minus a -1 is a +5. 2 minus a minus turns into a +1, which gives me a slope of a +5. Okay? Again, hardest thing here is just be careful with the signs. Okay? Again, let's call this x1, y1, x2, y2. My formula is the slope is equal to y2 minus y1 over x2 minus x1. So that is -2 minus 4 over 2 minus -3, which is -6 over 5. So that is -6 over 5. Good. Let's do a couple more from the checkpoint. Uh, let's keep the idea that we're going to go left to right. So now if we notice that this is x1, y1, this is x2, y2. Okay, but again, it does not matter. Okay, so the slope is equal to y2 minus y1 over x2 minus x1, which gives me 6 over a positive 1, which is 6. Last one, y2. Let's call this 1, this one 2. Okay, so y2 minus y1 over x2 minus x1 is going to be negative 7 over 5. So we have negative 7/5. Okay. So we can see that it doesn't really matter when using the definition of slope. How do you know which one to call x1, y1, and which one's x2, y2? When you compute slope, it makes no difference in which point you call 1 and which one you call 2. Okay? So if we let x1, y1 be negative 2, 4, x2, y2, the slope is still 5, right? Even though when we did it, we did this way, right? We called this one x1, y1, as opposed to negative 2 and 4 being x1, y1. So it doesn't matter. However, the biggest mistake you can make is to do this, y2 minus y1, x1 minus x2. So if you start with this point, with the y coordinate, you must start with this point with the x coordinate. That's the only thing you really have to be careful of. Okay? Now, when we look at slopes and how they act, okay, positive slopes are increasing and a line with negative slope is decreasing. So if we have a positive slope, we can see this line is rising from left to right. If we have a negative slope, we can see that this line is going down from left to right. Okay, and that's how this measure of steepness was evolved, right? Positives were going up, left to right. Negatives were going down. Zero slope is a horizontal change, and a vertical change is undefined. The slope is undefined because in that case, right, our formula means that if we are going to go vertical, it means that this change would be 0, which means we would be dividing by 0, which we are not allowed to do. Okay. So let's take that and let's use our first type of linear equation, right? It's called point slope. And in order to use point slope, you're going to need a point, you're going to need the slope. Okay? So we can use the slope of a line to obtain various forms of the line equation. So consider first this non-vertical line with a fixed point, right? x1, y1. This point could be anything. That's why it doesn't have a subscript, right? So if I want to find the slope, I'm going to have some x minus x1, some y minus y1, and I'm going to divide them like this. Okay? So my change in y would be y minus y1. My change in x would be x minus x1. This doesn't, regardless of where the point xy, right? The steepness of a line is always going to be the same. So the slope stays constant for any value of x and y. So if we mess around with this formula a little bit, if we take both sides of the equation and we multiply it by, right, here's my starting equation, my slope equation, multiply it by x minus x1, I now have an equation that looks like this. If we reverse the two sides, we now get the point slope form of the equation. Okay? And this is my point slope form of the equation. Y minus y1 is equal to m times x minus x1. Okay? Let's see how this works. So write an equation in point-slope form, right? So we're going to leave it in point-slope form for now. Usually we're going to maybe change it around a little bit, but for now, so what do we need? We need a slope, we need a point. So this is x1, y1, and that is m. My formula for point-slope form of equation is y minus y1 is equal to the variable times x minus x1. Okay? Plugging in, y and x are my variables, right? In order to have this line, this linear function, right, which we'll talk about in a little bit, in order to have this line, we need an independent and a dependent variable. We need an x, we need a y. Okay, so we're just going to fill in the other numbers so that way those are the only two variables that we have. So it becomes y minus y1, m times x minus x1. And we can clean that up a little bit and turn it into y minus 3 is equal to 4 times x minus a minus, turns into a plus. Okay? And that is the point-slope form of a line. Now the second part is solve the equation for y. Okay, so the first thing I'm going to do, is distribute the 4x plus 4, and then add the 3 to both sides to give me y by itself, 4x plus 7. Okay. This is the point slope form of the line. This is the next form that we'll talk about in a second called slope intercept. And it's also solved for y. Okay. Let's try again. It's my checkpoint. Oops. Slope, point. Y minus y1 is equal to the slope times x minus x1. Okay, so y minus a minus 5 turns into a plus 6 times x minus 2. Solve for y. So that's y plus 5, 6x minus 12. Subtract 5 from both sides. Y is equal to 6x minus 17. Point slope, slope intercept, solved for y. Okay, so let's write an equation in point slope form for the line passing through these 2 points, 2, 6, and 4, negative 2, 6, and 4, comma, negative 3. Well, before I can use point slope form, I need a point, which I have 2, and I need the slope. Okay, well, since I have the graph, I can find, this is a good point, it's negative 2, 6. I can find another good point. Oh, look, here's a good point. And I can figure out the change in y divided by the change in x. So to go from here to here, I would have to go down and then right. Down 3. So the slope is down 3. Right is positive. Right 2. Okay. If I didn't want to do that, if I didn't have the picture, I could always do what we did in the first problem. And again, it doesn't matter, but this is a good place to start. So y2 minus y1 over y2 minus y1, yeah, over x2 minus x1. So this turns into negative 9 over 6, which reduces to negative 3 over 2. Okay, so now I have the slope. Now I need a point. I got to pick a point, and then we're going to solve the equation for y. Let's pick this point right here. Okay, so y minus y1, minus turns into a plus. The slope, negative 3 over 2 times x minus 4. Let's solve this for y. negative 3 over 2x. That turns into a positive 6. Y is equal to negative 3 over 2x plus 3. Well, pretend I didn't want to pick that point. What if I pick the other point? So y minus 6 is equal to negative 3 over 2 x, parentheses x, plus 2. Okay, well, we're not starting at the same spot, but if we bring this and solve it for y, negative 3 over 2x minus 3, add 6 to both sides, and look what happens. Negative 3 over 2x plus 3. I get the same equation for both. Okay, so it doesn't matter which point you pick to use in the point slope form, right? You're still going to get, looks slightly different, but you're going to still get the same equation, and we can tell that by solving it for y so we can compare them. Let's do one more of those with the checkpoint. We don't have a picture here. So now we're going to have to use the slope formula to find the slope first. Once we find the slope, then we pick a point, then we solve the equation for y. Okay, so let's call this y x1, y1, x2, y2. So negative 6 minus negative 1 over negative 1 minus a negative 2. Again, trickiest part here is don't get messed up with the signs. So that's negative 5 over 1, which is negative 5. I'm going to pick this point for my equation. So y minus y1 is equal to m times x minus x1. Minus and minus turns them into pluses. Solve for y, 10. Subtract 1 from both sides. And we have y is equal to negative 5x minus 11. Okay. Which brings us to my next form of a line called slope-intercept. Okay. This is different than point-slope because point-slope can use any point. Slope-intercept, you have to use a specific point. So let's write the point-slope form of the equation of a non-vertical line with slope m and a y-intercept of b. So it's shown in a figure that I don't think I copied, but because the y-intercept is b, the line passes through a point 0, comma b, right? If we can think about a line, if we have some sort of slope, this point right here is going to have an x coordinate of 0 because I didn't go left or right, and then I'm going to go up and down some number b. Okay, so if I plug that point in to the point slope formula, I get y minus b is equal to m times x minus 0. Solving for y gives me distribute. Y minus b is equal to m times x. Finally, solve for y, we get mx plus b. So if an equation is written with y isolated on one side, the coefficient of x, that number, is the slope, and the constant term, that number, is the y-intercept. And this is called slope-intercept form of a non-vertical line. Y is equal to mx plus b. Okay. The slope-intercept form of a line's equation can be expressed in function notation, simply by taking y and changing it into f of x. So we can say f of x is equal to mx plus b. And we have seen that functions in this form are called a linear function. So in the equation of a linear function, the coefficient of x is the slope, the constant term is a y-intercept. Okay? Example, slope, intercept, slope, intercept. If y is by itself, or if it's in function notation, right, you don't really ever have function notation unless f of x is isolated on the left-hand side. if we're in function notation, the slope is always the lead coefficient, and the constant term is the y-intercept. Okay? And if it's in this form, we can use both of those to get the graph. Okay, so here's how we're going to graph if we have y isolated. Right? So if we have mx plus b, we're going to plot the point containing the y-intercept on the y-axis. 0, comma b, that number. Get the second point using the slope. We're going to write m as a fraction. So if it's a whole number, we're just going to put it over 1 and use rise over run. Okay, so we're going to go up or down first, then left or right, and we're going to start at the y-intercept point, and then we're going to draw the next point. And then, hopefully you have a ruler, we're going to use some sort of straight something to draw a straight line, and it goes forever in both directions. Okay, so let's graph this function, negative 3 over 2x plus 2. I'm going to start with the y-intercept. It is 2. There. That's not there. That's not the y-intercept. That's the x-axis. Okay. The coordinate is 0, comma 2. Okay. Then I use the slope. So that means, what does that mean? Well, it could mean this, down 3, right 2. It could mean this, up 3, left 2. It does not mean this, because then that would be positive. Okay, so it doesn't really matter. You can go either way, and let's do them both. Let's go down 3 from this point right here. 1, 2, 3, right 2. We can make a line with that. Let's try this idea. Up 3, 1, 2, 3, left 2, 1, 2. Okay. Still got a line. It's still going down. Okay. So now let's draw the line, and we put arrows on both sides, meaning that this line goes on forever in both directions. Okay, let's try it again. Our checkpoint here. Slope, intercept. Start at 1, go up 3, 1, 2, 3, left 5, 1, 2, 3, 4, 5. Or, right, 3 over 5, that's a positive slope. So is this. Okay, so if you happen to have some sort of graph where you can't go up 3, you could always go down 3. 1, 2, 3, and left 5. 1, 2, 3, 4, 5. My slope is positive. 3 over 5 is positive. This line is going up from left to right. Okay, and let's make a nice line. And we put my arrows at the end. Okay. This line, again, had a negative slope. It is going down from left to right, right? We look at lines this way, left to right, it is going down. Okay, so let's try this. Graph y equals negative 4. So if y is, let's think about this with a table. Pick a number, x, okay, anything, okay. Y is always equal to negative 4. It doesn't say anything about x. There's no input. The output is negative 4. The output is negative 4. The output is negative 4. So if I do this, if it's always negative 4, we can see that we have a line that travels from left to right, and it is horizontal. Missed it a little bit. There we go. Okay, that it is a horizontal line. So if I have y equal to something, I'm going to get a horizontal line. Yeah, go figure. Graphing a horizontal line. Let's try that again. Graph y is equal to 3. So I know it is going to be a horizontal line, and every point on that line is going to be 3. So it's going to look something like that with arrows at each end. Okay, so the equation of a horizontal line is always going to be y is equal to some number. And that number is going to be the y-intercept, right? The slope is going to be 0. So the x, so if we wrote it in slope-intercept form, right, if the slope was 0, right, this term just cancels out, and we have y is equal to b. Okay? Well, the opposite of that would be x equal to a number. And if I make a table, no matter, x always has to be 2. There is no output. So y can be anything I want. Doesn't matter. Okay? My answer, my input will always be 2, and there's nothing to plug it into. So when I look at this, and this one's a little weirder, but when I look at this, this turns into a vertical line. Okay? So that is x is equal to 2. I think we get the hang of this here. -3. So we would go to -3, and I would make a vertical line on -3, like that. Okay, so the equation of a vertical line is always x is equal to a. And you can see, even from my graph right here, it has no y-intercept. It never crosses the y-axis. Okay? So it does cross the x-axis, and so x is equal to a is a vertical line where a is the x-intercept, not the y. The slope of this is undefined, okay? Because it doesn't move left or right at all. Okay, so the last type of equation we're going to do is general form. The vertical line whose equation is x equals 5 cannot be written in slope-intercept form because the slope is undefined. However, every line has an equation that can be expressed in the form ax plus by plus c is equal to 0. So x is equal to 5 can be expressed as 1x plus 0y minus 5 is equal to 0, or just x minus 5 is equal to 0. The equation ax plus by plus c is equal to 0 is called the general form of the equation of the line. Okay. Also, we can use standard form, which is going to be similar, which is ax plus by is equal to c. Okay, we can just move the c to the other side. We're going to try to get into a habit in later in this course of setting things equal to 0 to provide solutions. So we're going to get into the habit right now with the lines. So we're going to tend towards general form as opposed to standard form for this particular text. Okay. So let's find the slope and the y-intercept of the line whose equation is 3x plus 2y minus 4. Let's write this down. 3x plus 2y minus 4 is equal to 0. So I can't really tell just by looking at this, because it's in general form. If it was like this, I could easily tell the y-intercept and the slope. So we solve for y. So we have 2y is equal to, subtract the 3x from both sides, add the 4 to both sides. And now divide out the 2, making sure to divide everything by 2, not just one term. So it's -3 over 2x plus 2, not 4, which makes my slope -3 over 2 and my intercept +2. So if I wanted to graph this, I would start there, go down 3, right 2, and I would have my line. Let's do it again with a checkpoint problem. 3x plus 6y minus 12 is equal to 0. Subtract 3x from both sides. Add 12 to both sides. Gives me 6y is equal to -3x plus 12. Divide everything by 6. You can do it this way too, if you feel better than putting them over one fraction. Y is going to be equal to -1/2 x plus 2, which makes my slope -1/2, and my y-intercept, again, So another way to graph is so before when we did 7, right, that was graph aligned equations to convert it to slope-intercept form and then use a slope and a y-intercept. So we could do that if we wanted to. Another method is to use the intercepts. So we don't have to change general form at all. We can find the x-intercept by letting y is equal to 0. Put the point on the x-axis. We find the y-intercept by plugging a 0 in for x. Put this point on the y-axis, and we only need 2 points, so now we can draw the line. Is this method better? Personally, I usually just default to solving for y and using slope-intercept form, but you can use this method if you want to. Okay, so here's my equation: 4x minus 3y minus 6 is equal to 0. Okay, plug 0 in for x, and then we'll plug 0 in for y. Okay, so let's find the y-intercept first. So I'm going to plug a 0 in for x. Okay, that cancels. Negative 3y is equal to a positive 6. So y is equal to negative 2. So that gives me a coordinate of 0, negative 2. Okay, that's right there. Okay. Next, plug 0 in for y. Let's get a little more room. Okay, that cancels that. 4x is equal to 6. Divide out the 4. X is equal to 3 over 2. So that gives me a point of 3 over 2 comma 0. So that's 3 over 2 comma 0, which is 1.5. Okay. Didn't work out perfect. That's okay. And now we just connect the dots with a straight line. Arrows at the end, and we're done. Okay. So maybe you found this method to be a little bit easier with intercepts. Maybe you like to just solve for y and use slope-intercept form. Okay. Either way, it is fine. Let's try one more. Okay. Oops. Three x minus 2y minus 6 is equal to 0. So let's plug 0 in for x. That gives me negative 2y is equal to a positive 6. Divide out the negative 2. And we have y is equal to negative 3 to give me a point of 0, negative 3. Okay. 3x minus 2y minus 6 is 0. Let's plug 0 in for y, which cancels that out. 3x is equal to 6. Divide out the 3. So x is equal to 2. This one works out a little bit better. So this is 2 with a 0 for y. So 0, negative 3 goes there. 2, 0 right there. Very similar line to the first problem. And we make our nice line. Okay. So again, if you want to solve these equations using the intercepts, this is a method, right? Finding this intercept, connect the dots. If you want to use slope-intercept form, you can use that as well. If you want to use point-slope form, that's a technique as well. Okay, so we've covered a lot here. Let's take a moment to summarize the various forms of the equations. Point-slope, y minus y1 is equal to m times x minus x1. Slope-intercept, either in xy notation or function notation. Y is equal to mx plus b. Horizontal lines are y is equal to a number. Vertical lines are x is equal to a number. General form, one thing to mention about general form is we want a, b, and c to not be fractions. Okay, so we're going to clear out any fractions if we do have any fractions. Okay, and so general form, we're going to just have these coefficients times the variables plus this constant term set it equal to 0. Let's use this in an application. So linear functions are useful for modeling data that fall on or near an actual line. So let's just try one of these. and let's model global warming. So let's walk through this problem because there's a lot of information here. So the amount of carbon dioxide in the atmosphere, measured in parts per million, has been increasing as a result of the burning of oil and coal. The buildup of gases and particles that traps heat and raises the planet's temperature. The bar graph at the down here gives the average atmospheric concentration of carbon dioxide and average global temperatures for the 6 selected years. The data are displayed as a set of 6 points in a rectangular coordinate system for this one. So if we look at these two graphs right here before we start looking at the questions, okay, we have global temperatures versus carbon dioxide concentration parts per million, and we can see what happens over different years, okay? And if we were to plot those different points, you can see that this line doesn't go perfectly through it, but it's an approximation of all the data. So shown on the scatter plot is a line that passes through or near, right? It's kind of close to this one. It's close, it's close, it's close. Okay? So it's near all the other points. Write the slope-intercept form of this equation using function notation. Okay. So how are we going to do that? Well, if we want slope-intercept form, I don't have the intercept, but I do have a point, and I do have another point, so I could use those 2 points to find, right, we want to find the slope-intercept form of this blue line. We're not going to worry about the other points too much, okay? I'm going to use my equation. Okay, so my equation is y2 minus y1 over x2 minus x1. This will find me the slope of the line, and then I'm going to pick one of those points and use it to write the equation. So y2 minus y1, let's go back up here, 57 and 57.99, 57.06. So 57.99 minus 57.06 over 385, 326. 385 minus 326. This gives me about, right, I'm not going to go crazy here, it gives me 0.93 over 59. When I divide this, again, let's round it to 2 decimal points, and we get 0, we get 0.02. Okay, so that's my slope. Right. Now all I have to do is just pick out one of the points. Doesn't matter which one. Let's use this point. Okay, so y minus y1, 57.06, is equal to the slope 0.02 times x minus 326. Okay. Let's distribute is equal to 0.02x minus, again, 2 decimal points is fine, 6.52. Add 57.06 to both sides, and we get y is equal to 0.02x, adding 57, 50.54. Okay. Okay, so that is the slope-intercept form of the line. If I want to use function notation on that, I can easily just swap out this for f of x is equal to, you got 0.02x plus 50.54. Let's look at the next part of this. The pre-industrial concentration of atmospheric carbon dioxide was 280 parts per million. United Nations Intergovernmental Panel on Climate Change predicts global temperatures will rise between 2 and 5 degrees if the carbon dioxide concentration doubles from the pre-industrial level. compared to the average global temperature of 57.99 for 2009, how well does the function from part A model this prediction? Okay, so here was this data point. Whoops. Here was this data point right here, which is where those numbers coming from. Basically, this question is saying, if we double this, does this function come close enough, right? In between 2 and 5 degrees Fahrenheit, if we double our 280 parts per million. Okay, so let's do that and let's plug it into the function. So first, doubling 280 gives me 560, right? So if we say that x is equal to 560 and we plug it into my function, so f of 560 would be 0.02 times 560 plus 50.54. Plug that into a nice calculator, and we get 61.74 degrees. Right? I'm skipping out on the symbol signs here, or symbols. So our model projects 61.74 for a carbon dioxide of 560 parts per million. If you compare that with 57.99, we get about 3, almost 4 degrees different. Okay, so this is consistent with between 2 degrees and 5 degrees if this model was actually predicting anything. Okay, so let's wrap this up here. So we talked about how to find slope. We talked about point slope form of equation line, slope intercept. We graphed some vertical lines, we graphed some horizontal lines. We used the general form. We used the intercepts to graph an equation, and we did a crazy word problem with some global warming. Okay, so that was 1.4 linear functions and slope. As always, if this video was helpful, please like and subscribe to the channel for all the new videos that I post for pre-calculus content. Thank you very much.